So in this NMOS inverter example, we are asked to find the transition point, minimum output voltage, maximum drain current, and maximum power dissipation for this NMOS inverter, given that the NMOS inverter has registered load. That is, load means that the VDD and the VDS are actually the output terminal is connected through this RD resistance. So for this N MOSFET terminologies, we are going to use this RD resistance as load. So the thing that is connected between the VDD and the output terminal will be considered as load. That is quite different from the definition of load we have seen before. Okay. So the first thing is we need to find the transition point. So the transition point is defined as like whenever the VDS is equals to VGS minus VTN. So this is the drain voltage, what we consider as the transition voltage. Okay, so now when the MOSFET is operating in transition point, we could consider it as operating in, let's say, saturation or triode. It doesn't matter. So we will use the saturation mode because the formula for saturation mode is much simpler. So we have so the drain, the formula for the drain current would be the VDD is here 2.5 minus V0 divided by 20, because this is 20 kilo ohm, RT is 20 kilo ohm, equals to, the formula should be Kn VGS minus VTN square. So Kn is 0.3. We know the value for VGS, that is, for this condition, this should be 2. The input is actually unknown because we don't know what should be the input voltage, so that we have this case that we should write like this: Vi minus the threshold voltage 0.5 square. Okay, so as we have discussed that VDS should be VGS minus VTN. So this is actually VGS minus VTN. So we can replace it like 0.3 with VDS, and VDS here is V0. So V0 square. Now we can simplify this formula and we will get 6 V0 square plus V0 minus 2.5 equals to 0. Now the solution for V0 would be 3.4051 and 0.5675 voltage. So we can now check which actually satisfies our transition point condition, and it is beyond doubt that 3.50 would not be answer, because this is greater than 2.5, which is the maximum voltage in this configuration. So we can cross this out. Therefore, this should be our output voltage when the MOSFET is operating in transition point. So this should be our output transition point voltage, or VDS. Okay, so now we need to figure out the minimum output voltage and the maximum drain current here. Okay, so now for minimum output voltage, we need to think about when the output voltage will be minimum. So if we increase the, let's say this is an inverter, so therefore whenever the input voltage is maximum, then the output voltage should be minimum. And the maximum allowable voltage for this configuration should be at least about the VDD, because in usual circuit design we know that we connect the maximum voltage to VDD terminal, so therefore it must be the maximum voltage we could apply to the gate terminal. So we would get the minimum output voltage when the input voltage is 2.5. So we are going to use input voltage as 2.5. That will give us the minimum output voltage. Minimum output whenever we are using maximum input for this inverter circuit. Okay, so because input voltage is now 2.5, so we can safely assume that M1 is operating in triode region. Okay, so M1 is operating in triode region, and eventually this will give the maximum drain current. So this condition will, however, give us maximum drain current, because you could remember it from the drain voltage relationship. Whenever the drain current, whenever the gate voltage is higher, then the drain current will go up. Okay, so let's calculate this one. So we have drain current IT equals to 2.5 minus V0 divided by 20 equals to the, we should use the formula for triode region, and if we plug in those formulas you will get 0.3 2 times 2.5 minus 0.5 V0 minus V0 square, and this will lead us to this quadratic equation, that is 25 V0 plus 2.50, and eventually we'll get the output voltage equals to 0.1025 volt and 4.064. So the VDD is 2.5, and we can safely eliminate this choice. So we should use the V0 equals to 0.125 volt, and now let's check whether it satisfies our assumption that M1 is operating in triode. So for this case, we will have VDS 0.1025, which is less than VGS, that is 2.5 minus VDS 0.5. So it satisfies the condition for triode region, therefore our assumption is correct. And now we can calculate the drain voltage. So drain current should be, we can plug in the output voltage here, and we will get the drain current equals to 0.125 0.1198 milliampere. And again, for the power consumption, this should give the maximum power dissipation for this NMOS inverter. So the power dissipation would be just the multiplication, because the current is flowing from 2.5 5 voltage to this ground, and there is no current is flowing through the gate terminal. So therefore it is very easy to calculate the power dissipation here. 2.5 times 0.1198 milliampere, and the power dissipated power should be around 0.3 milliwatt. Okay, so now let's do a different type of example, that is NMOS NOR gate. So here you have the structure for the NMOS NOR gate, and in this problem we are asked to determine the current and voltage in this digital logic gate for various input conditions. So because this is a digital logic, we are going to actually use only the logical high and logical low voltages for input voltage. And for our discussion, our case 1 should be like when the input and when the both input voltages are 0. Whenever the both input voltages are 0, then we can clearly see that the input voltages or gate voltages are less than the threshold voltage. And that means that none of this transistor will turn off. So all these transistors will turn off, and therefore the ID1 equals to ID2 should be 0 milliampere. So there will be no current flowing through this two transistors, so two MOSFETs, and that will lead us the output voltage is equals to the VDD, because there is no current flowing through the RD. So now V0 is equals to VDD or 5 volt. Now let's move on to the case 2. Case 2 is somewhat symmetric. We are going to consider one input voltage high and another input voltage low. So we could pick V1 is high and V2 is low, or V2 is high and V1 is low. That would make any difference, because the internal parameters such as Kn and Vtn is same for both of these two transistors. But in your homework problem, you will see that M1 and M2 might have different internal parameters or conduction parameter and threshold voltage. Then you need to actually consider this case in two different section, that is V1 is on and V2 is off, and another one is V2 is on and V1 is off. So in our case, we just pick V1 is on and V2 is 0 volt. So therefore V2 should be in cutoff. There is no doubt about it. And V1, from our experience, we already can tell V1 should be in triode. Because V1 is operating in triode region, then we can use the formulas for triode region, and we just consider this part is inactive. Therefore, ID2 is 0 milliampere. Now we have IR equals to ID1. This is just like a typical inverter circuit, because this left side, the right side is now actually inactive for this input condition. So it will give us the formula like 5 minus V0 divided by 20 equals to 0.1, that is Kn, 2 times. Now the input voltage for V1 is now 5. So 5 minus VTN, that is 0.8. VGS, so this is unknown, VDS minus V0 square. So if we simplify this formula, we will get something like this. 9.4 P1 plus 5 equals to 0. And finally, we have V0 equals to 8.6, and another one is 0.29. We can eliminate this one because this is greater than the VDD voltage. So the answer should be 0.9. And using V0, we can calculate easily the drain current. That should be 5 minus 0.29 divided by 20, and the solution is 0.2354 milliampere. Okay, so now we can consider the final case, that is when the two input voltages are high. Okay, so case 3, that should be V1 equals to V2 equals to 5 volt. In this case, the actual formula would be IR equals to ID1 plus ID2. Okay, so because both of these transistor is now in is actually turned on, so therefore we need to add up these two current to get the value of IR. So now we cannot actually cross out any one of these transistor and calculate the whole thing. So now this is going to be 5 minus V0 divided by 20K, and the ID1 formula is just 0.1, 2 times 5 minus 0.8 V0 minus V0 square, and the same formula would be for M2 transistor because all of these parameters are same. So we can actually repeat this one here, or we just multiply this one with 2. But if these two transistors are not symmetric, that means the internal parameters Kn and Vtn are not same, we need to actually write it down. Okay, so for this case, both are same, so we can multiply 2, and this, from this we will have a formula, quadratic formula, 34.6 V0 plus 5 equals to 0, and it will give V0 equals to 4.17 and 0.149. Okay, so now which one we should pick? So we are actually using M1 and M2 is operating in triode region, and you can see 4.17 would not meet this criteria. So if the output voltage would be 4.17, then both of these transistors will operate in triode region. Okay, so therefore this should be the correct result, 0.419, and the triode region condition would be satisfied if we use the output voltage is as 0.149, and from this we can calculate the ID1 from here. Oh, sorry, this should be IR. So first we calculate the IR, or the current through this resistor. using 5 minus V0 by 20, it will give us 0.243 milliampere. And we know because of the symmetry, the current would split into equal parts through this M1 and M2 transistor. So ID1 equals to ID2 should be IR by 2, and that is 0.121 milliampere. Okay, but if the internal parameter of M1 and M2 would be different, then we couldn't divide it equally. We need to use this. You need to use this formula to actually separately to find out the values for ID1 and ID2. Okay, so next we are going to change this resistance, and we will put some different type of loads that would be called enhancement type load or depletion type load, and we are going to see what would be the output voltage for these conditions.